Energy diagrams in 10.7. This time, only isolated systems. There is no friction and no drag, so that means no work and no change in thermal energy. So the work energy equation can start off like this. E equals just kinetic and just potential, and everything is constant in the system. So that's great. So kinetic energy depends on an object's speed. Potential energy depends on its position. A tossed ball's potential energy depends on its height, y. The compressed spring's elastic potential energy depends on the displacement, x. Other potential energies depend in some way on position as well. So as long as we remember those things, we'll be in pretty good shape. We can have a graph showing a system's potential energy and total energy as a function of position, and that will be called an energy diagram, and that's what this section is all about.
Have we? No, never mind.
No?
No.
Okay. So the energy diagram of a ball in free fall here is shown. Notice, first of all, the scales that we're talking about here. We have, since it's a ball in free fall, we would be talking about with a y position. But notice that y is on the horizontal axis. Okay, so as the ball is falling, its y position is changing. And so that is on the horizontal axis because we're talking about its change in energy, and we're putting that on like the y-axis, but it's not the y-axis, right? It's the energy axis. So that's kind of confusing, but remember that we're putting energy on the vertical axis.
It makes sense though.
Yeah.
Because your energy is increasing. If you had it the other way, it would be decreasing.
Yes. So the variable is energy that we're talking about here, as the energy is changing. So the total energy line here is constant, okay? The total energy is constant. As the ball falls, the potential energy is changing and the kinetic energy is changing. But the total energy is remaining constant because we're considering that there is no friction, there is no drag. It's almost like there's no air, right? So we're not losing any energy at all in this system. So the total energy remains constant. And that's why this line is horizontal. The energy line here is horizontal. Now, as the ball falls, we're picking up kinetic energy and we're losing potential energy. So the potential energy situation versus the kinetic energy situation should add to the total energy line that we have. So we see the kinetic energy increasing. So kinetic energy here is increasing, and the potential energy would be decreasing as the ball falls. Okay, so down here we have the kinetic and potential due to gravity change as the particle moves from y1 to y2, but the sum is always E. So the sum, energy equals kinetic plus potential up there, is always going to add to the total potential energy. So now the potential energy curve here, how come we see the potential energy line, the line that's there, how come the line is climbing? What?
Because energy starts out, I don't know.
Is it because this ball's getting tossed in the air? No, because it says it's in free fall.
Ball's in free fall, but that doesn't mean, like, when I throw something into the air, the second that it leaves, the instant that it leaves my hand, it is immediately in free fall. It does not necessarily need to be falling.
Well, because it shows that your potential is increasing, right? In that diagram.
It does show the potential is increasing.
So then it'd have to be tossed in the air.
Is it? Because it's all constant. I don't know.
Is it a diagram of the kinetic energy? It starts off in nothing and then it speeds up and speeds up, and starts getting bigger and bigger and bigger.
What is on the horizontal axis?
The y-axis.
So the y, the position of the ball from the ground. So what is this position over here?
Zero.
Zero.
Okay, so where would the ball be then?
On the ground.
It would be on the ground. Where is the ball over here?
It's somewhere in here.
Somewhere in the air. Okay. So then what happens when the ball is way up here?
It has a greater.
Potential increases.
It should have maximum potential energy at that point, right? So I could throw the ball up into the air, but when I throw the ball up into the air, where would the ball be on this curve? It would be over here somewhere, right? Then the ball goes up into the air, and so it's going to climb along this curve until it reaches its maximum height,
And then it's going to.
and then it's going to go back down, which means then it's going to come back down this curve. Okay?
Wait, so you wouldn't draw off of that like another curve coming down?
No, I would. It would not come like it would not do
Oh,
this.
because you would be you'd still be increasing the y that way,
Yeah,
which would not.
because it's not going to go farther up. It's going to go up, and then it's going to come back down. And then if I throw it again, it's going to go up, and then it's going to come back down. It does not go farther along because that would just indicate that it went higher up. Okay.
And it's
So like I said in the very beginning, reading this graph is the tricky part. Once you understand we have a maximum height that we can go, we can only go a certain distance along this graph. We have to go up and then back down.
so then okay. How come k is on one side and u is on the other? Does that show that like the underside of the graph?
Now that we understand where we can go on this graph, now we can read the rest of it. Okay. So now we have how much kinetic energy do we have when we first throw the ball?
0.
When we first throw the ball,
Oh, when you first you have a lot.
we have a lot of kinetic energy. So this gap right here is all of the kinetic energy that we have. How much potential energy do we have? Not a lot at all, right? So this gap right here is all of our potential energy. When we get up to our maximum height, how much kinetic energy do we have?
0.
Not a lot.
Not a lot, almost none, or at the maximum height, we have no kinetic energy. So this gap right here is still our kinetic energy. How much potential energy do we have?
A lot.
A lot, or at the maximum, all of it, right? So this gap right here is all of our potential energy, okay? So the gap here, kinetic energy, plus the gap here, potential energy, equals the total energy, okay? So that's how you read that graph. So now we step it up a little bit on this one. We have the energy diagram for a mass on a horizontal spring. So picture in your mind, we have something connected to a spring. Maybe it's connected to a wall, and we just push on the spring, and then it's sitting there oscillating back and forth. So the energy of the system, we have the total energy curve sitting here. The potential energy curve looks more like a parabola now. The height of the energy line is determined by how far you stretched or compressed the spring in the first place, and now it's just sitting there oscillating back and forth. So if I stretch maybe I stretch the spring a little bit, then the energy curve would be lower to start off with, okay? Maybe it would be down here. If I stretch the spring way farther than what this is shown now, then my energy curve would be up here instead, okay? As it stands right now, we have this energy curve. So let me get rid of those lines. And so we're looking at this energy curve now. So we have a mass on the horizontal spring. It's oscillating back and forth. It can go from here to here, and that's it. Okay, so it's just oscillating back and forth. No friction, no drag, no nothing. It's just oscillating back and forth for forever.
So if you don't have those, it would do that. Like if you didn't have any outside forces.
It would just sit there and go back and forth for forever. Yep. Okay. So up to this point and around back to this point, okay? And that's it. Now, like I said, if there's going to be a longer stretch, then we're going to be able to go up to maybe this point, and the energy curve would be up here instead, right? Totally straight line there. Okay, so now the blue potential energy curve is given by this equation right here. It's centered at 0, so this would be the equilibrium point where the spring was at rest. And so we set our parabola at that point. The potential energy curve is given by the spring constant, which is K. We can't change that. If we change springs, we could change it, but we can't change it for this situation right now. We can see the energy line. We can set that to any height by stretching or compressing the spring to different lengths. So in this figure, we see one possible energy line. So suppose we pull the mass out to a position x sub r and release it from rest. That's what I'm talking about, where we just change the position, the initial position that we pull it out to will change the energy line, right? So here, at some point, we let it go, and maybe we like take a picture, we stop the motion somewhere along the way, and maybe the spring is, or the mass is sitting right here at that point. So that means we have that much potential energy. So right here is the potential energy that we have at that moment, okay? Which means right here is the kinetic energy that we have at that moment, okay? So then right there, that is always the total energy, potential energy plus kinetic energy, okay? So we know that we're in motion in one direction or the other. So then we add those two things together, we have the total energy. Over here, we have almost all potential energy and almost no kinetic energy. Down here, we have almost no potential energy, almost all kinetic energy. So we're moving almost as fast as possible. So that's how you read that, okay? The curve is the potential energy curve. And then what's left over is all kinetic energy. Is that making sense?
Would kinetic ever be where potential is?
Would kinetic ever be where potential is? What do you mean?
Like, so you have potential here and kinetic here on the other side of the line. Would it ever be flip-flopped where potential is this way and kinetic is this way? Or no? Is that not a possible scenario?
In order for that to happen, you would have to have more potential energy than you have energy in the first place. And that can't happen. Okay. So here are 5 possibilities. So this is what I was just kind of talking about. We have the spring. We pulled it out to x sub r, and then we're going to release it. Okay, so right now the velocity is 0. We're going to release it from this position and then let it go. Okay, so we pull it up, we let it go. So it has now that total energy in the system. So we let it go. Its velocity is now going towards the wall. So it now has released a lot of that potential energy. It's now left over with kinetic energy. It has very little potential energy. So it's moving pretty quickly. At this point now, it's moving its fastest. Notice its position is back at the equilibrium point, and it has no potential energy. It's all kinetic energy. And then we have, at this point here, where are we?
What?
Which way are we going?
Still going back towards the wall, right?
Still to the left.
Okay, still going back, but we're no longer going at our fastest velocity. We're gaining some potential energy back. We're losing some of our kinetic energy. And then at the 5th point, our velocity has reached 0. We have no kinetic energy anymore. We have all of our potential energy back, and we're about ready to turn around and go back the other way. Okay?
Without drag or air resistance, would this cycle keep repeating?
Yes. In the theory is without drag or air resistance or any kind of internal. Internal. No external forces, no internal friction or anything like that. Then yes, this would oscillate for forever. Okay?
Like in close, we could actually test that scenario. But.
Yeah. So the answer is no in reality, but yes, theoretically. Interpreting an energy diagram. So here we go. This is a more general energy diagram. We don't know how this potential energy was created, but we can still use the energy diagram to understand how a particle with this potential energy will move. Suppose a particle begins at rest in the position shown in the figure and then is released. Describe its subsequent motion. So what's going to happen here? So remember, the curve is potential energy.
So this would be a spring because it will be this triangular shape.
So what do you think is going to happen first?
It's going to roll down the hill, then go up the hill, and then go down the hill, and then go back up.
This is a ball rolling down a hill, you think?
Could be.
Certainly it says the particle was released right there, so that would be your energy line, wouldn't it?
Okay, so first of all, let's look at some key moments here. we have a key moment right here.
Relative minimum.
So we can call they call that x sub 1, so we'll call this x sub 2. We have a key moment right here. We'll call that x sub 3. And then we have another key moment right here. We'll call that x sub 4. And then we have another key moment right. I'm going to do something here. One final key moment happens here.
So you just drew your energy line.
I needed an energy line because that's where we released the thing from rest, whatever it was. Okay, so let's describe what happens here.
So at the start, you have a lot of potential and no kinetic.
All right, so what happens to the object, whatever it is?
It's being pulled, if it's a spring in this case.
Doesn't matter what it is, if it's a spring or if it's something falling or whatever it is. What is going to happen?
Be a spring because it's in a parabola shape.
We don't know.
Could be a ball rolling down a hill.
Could be something rolling down a hill. It could be anything. What is it? What's
Also
happening?
getting punched in the face.
Well,
Regardless, what is it? What's happening for sure?
You have
It has
kinetic. You're gonna have a lot of kinetic. Then it's gonna be released into a little bit of potential.
Okay.
And then a lot of
In words that somebody in the hallway would understand, what's happening?
It's like
it has a lot of.
It's going up and down.
In terms of speed, what's happening?
Its speed is
Speeding
zero.
up and then slowing down. And
Speeds up. Okay, and then what?
Slows down.
Slows down. Then what?
Speeds up again.
Speeds up again.
speeds up to max the rate.
Okay, and then what happens right there?
It has no speed, right?
No speed?
Maximum speed.
Max speed.
Wouldn't max speed be closer towards energy? I'm confused by that.
Because the kinetic is at
Oh,
the
the
top,
kinetic,
so
okay,
the
yeah.
biggest
And then it slows down until it goes back to zero.
goes to rest.
Okay, so we're slowing down here. Okay, and what happens right here?
Stop at rest.
At rest. And what would happen if it continued?
It would then have the same thing repeat.
It would go down.
So,
and get the maximum.
so this is a turning point. And what is this line called that I drew?
Energy.
That's the energy line. Okay. So that's the idea. You can pick out where it is moving its fastest, where it's at rest, and so on. Okay. What if I moved this object down to here?
And that's where it started.
What if I released it from right there?
Then you have an energy line.
I would have a new energy line.
It wouldn't get
would
past
repeat
that.
the same thing.
It wouldn't get past that relative minimum or relative maximum.
And because of that new energy line, I can see that it would not make it over that first little hump right there. It would actually come to rest right here, and we would not have enough energy to make it past that first rise. It would never go, and it would just go back and forth in that first little bit. Okay? Not enough energy. I would have to raise this up to at least like there in order for it to have enough energy to make it over. Okay?
Please tell me you don't have to draw these.
Yeah, you have to draw them. So that's how the energy diagram helps us. I can see from this energy diagram that I have to have enough energy to make it over this rise right here in order for me to make it over and get into this little maximum speed area here and be able to oscillate back and forth. Okay? That's one way it can help us anyway. Okay, so equilibrium positions. This is actually a very important concept here. Places in an energy diagram where the potential energy has a local or relative. Both of these words here can be used, local and relative. They mean the same thing. Minimum or maximum are important positions. They are potentially equilibrium positions, places where you are stable. or unstable at rest. Unstable would be barely able to hang on, but you are hanging on. Stable would be you're hanging on and perfectly able to just kind of like rest easy, okay? At rest, so stopped. So positions of A, unstable, and B, stable equilibrium. So in A, we have the particle at position x3 with energy E3. This is an unstable equilibrium position. Think like you're at the very top of a peak, like you're a rock climber maybe, and you're standing at a very, very, very tip top of like the pinnacle of some very narrow, tiny little thing that you climbed up on top of. It's like 100-foot tall, and you are 1,000-foot tall. I don't know, and it's like only like 6 inches wide, and you're just barely hanging, like just there, right? And then a gust of wind blows up. Are you going to feel pretty comfortable with being up there? Probably not, right? You're just going to fall off at any moment. That's very unstable. That's this right here. Okay, you don't want to be up there. You're just going to fall off at any moment. If a little gust of wind comes up, it's going to blow this little dot one side or the other pretty easily. Okay, that's an unstable equilibrium. That's trying to balance your pencil on the sharpened end on the table. It's even if you got it to do it, it would fall over at just at a slight breath. So that's unstable equilibrium. Stable equilibrium, on the other hand, is something like this. Okay, that would be your pencil on its side, very, very stable. Okay, no problem there. So another one down here, also stable equilibrium. That's where we want our equilibrium positions to be. Very stable, no problem. The particle is at rest with no kinetic energy. So it's just sitting there at each position. X3, unstable. X2 and X4, very stable. The marble on a hill, unstable. Balanced rock, unstable. Pencil on its edge, unstable. Slight disturbance only raises the ball up to here. So if we were at X4, a slight disturbance, maybe it pushes us up to here or here, but right away we come right back down. Okay, no problem. Up here, slight disturbance pushes us to one side or the other, and immediately we fall. Okay, that's a big problem. So the unstable equilibrium, it is equilibrium, but it's a slight disturbance and we're done. So that's the idea. Equilibrium positions, they are all equilibrium. What do they have in common? What do all these equilibrium positions have in common?
They're at
Equilibrium. They're at equilibrium.
But how do you know? How can you pick them out easily just by looking at the graph?
Because there's a turning point.
Because they're on the
What do you mean by turning point?
Like, you can plainly see that, like, it turns, and now you're either getting.
How can I pick out the turning point though?
It's on the E line.
It's not though. X4 is not.
They're at the tops or bottom of humps.
They're at maximums and minimums.
They're at maximum and minimum. The graph here goes horizontal. Horizontal, horizontal, horizontal. Okay? So that's kind of how you pick them out. And yes, maximum and minimum values, definitely. But they don't have to be. Okay? For example, I could do this, right? I kind of did a bad job of drawing that. But the graph goes horizontal right there. At least I tried to get it to go horizontal. That's not a maximum or minimum, but the graph went horizontal. Okay?
It's an x to the third type of situation.
Yes. Okay, so that's the idea. Now, the figures below show blue potential energy curves and tan energy lines for 4 identical particles. Which particle has the highest maximum speed? What do you think?
B.
Agreed.
Everybody thinks B. Why?
Starts the highest, goes the lowest.
Because the gap
draw your potential and your kinetic, and you'll see that that one obviously has the greatest kinetic energy at rest.
All these.
That's the one. So B starts the highest. So it has the highest energy line with the biggest gap. So this gap right here is kinetic energy. And even though this one here, D, starts highest, right? It does not have the biggest gap. So the one with the biggest gap is the winner. So B is the winner.